In this skill, we're again calculating the change in Gibbs free energy for a reaction, except this time we're also using an energy profile to find our enthalpy change of reaction. In this particular question, a scientist wants to predict the change in Gibbs free energy of a reaction, delta G naught reaction, for a fictional reaction involving fictional elements with the symbols E, Q, D, and L at a temperature of 5,300 Kelvin. We're told for this reaction, delta S naught of reaction, that's our entropy change of reaction, is 0.0105 kilojoules per Kelvin mole. And we're told the reaction is described by the energy profile provided. So here's our energy profile. We've got potential energy in kilojoules per mole on the y-axis, reaction progress on the x-axis, and we can see we start with our reactants here, and we end up with our products here. So our first step is going to be using this energy profile to find our enthalpy change of reaction. So we want to see between our products and our reactants, what was the change in energy. So we start out with our reactants at 20 kilojoules per mole. Then our products, those are at 70 kilojoules per mole. And we can see our reactants are lower than our products. So this is going to be a positive enthalpy change. And we started at 20, we ended up at 70. So it's going to be 70 minus 20. That gets us 50 kilojoules per mole. So let's go ahead and fill in our known variables in here. We just calculated the enthalpy change of reaction was 50 kilojoules per mole. Delta S naught of reaction, the entropy change we were given in the question as 0.0105 kilojoules per Kelvin mole. The temperature we're given in the question as 5,300 Kelvin. So let's go ahead and find our Gibbs free energy equation from the reference sheet. Here it is, our Gibbs free energy in terms of enthalpy and entropy. So delta G naught is equal to delta H naught minus T delta S naught. Remember, our temperature must be measured in Kelvin. So we've got delta G naught is equal to delta H naught minus T times delta S naught. So this is already arranged for delta G naught, so we can go ahead and put in our numbers. Delta H naught, our enthalpy change was 50, minus our temperature, which is 5,300, multiplied by delta S naught, our entropy change, which was 0.0105. So if we put this into our calculator, we're going to have 50 minus 5,300 times 0.0105, which gets us minus 55.65. So when we put that all into our calculator, we get a delta G naught of negative 5.65 kilojoules per mole. So we can go ahead and fill that in, negative 5.65 kilojoules per mole. What drives this reaction? Now remember, something that drives the reaction is something that makes delta G naught more negative. So that could be that our delta H naught is negative, since that being negative in our equation would make delta G naught more negative. Or it could be that our delta S naught is more positive. Since that being positive, it's then subtracted, that would make delta G naught more negative. In this question, we have positive delta H naught reaction. So that's not contributing to a negative delta G naught. However, we have a positive delta S naught, and when that gets subtracted, that is contributing to delta G naught being negative. So it's our entropy only that's contributing to our reaction. So we had negative 5.65 for our delta G naught of reaction, our Gibbs free energy change. So finally, we need to determine if the reaction is thermodynamically favorable or unfavorable in the forwards direction. Well, since delta G naught is less than 0, that's telling us our reaction is thermodynamically favorable, and therefore it's going to be spontaneous in the forwards direction. So in this question, it works exactly like the previous skill. We're still using our change in Gibbs free energy equation with the change in the enthalpy, the temperature, and the change in the entropy. However, this time you're also going to need to use an energy profile to figure out our enthalpy change of reaction.